You know, sometimes the biggest revolutions in science don't start with a huge explosion, but with something as simple as a quiet glow. Today, we're going to follow the story of one single elegant equation that didn't just bend the rules of physics, it completely smashed them wide open. It revealed that the universe, well, it isn't anything like what we thought it was. Okay, so here's our game plan. We're going to start with a simple glowing object that had the smartest people on Earth totally stumped. Then we'll see how that little glow proved that physics itself was basically broken. After that, we'll dive into the radical idea that fixed it all, uncover the universe's secret recipe hidden inside a tiny formula, and finally, see how this one idea literally changed the world. So it all kicks off with a question you've probably wondered about yourself. I mean, if you've ever seen a blacksmith at work or even just looked at the burners on an electric stove, you've seen this happen. The hotter something gets, the more its color changes. Seems pretty straightforward, right? Well, for the physicists back in the 19th century, this simple observation was a complete and total mystery. And that's the real kicker. The laws of physics they were working with, the brilliant ideas from giants like Isaac Newton, were supposed to explain pretty much everything. But when they pointed that math at this simple glow, their answers weren't just a little bit off. They were catastrophically, fundamentally wrong. So what exactly was this glowing problem? Well, to really get it, we need to talk about something called black body radiation.
Yeah, the scientific name for it is black body radiation. It's a kind of weird name, I know, but the idea is actually super simple. It's just that anything with any heat at all is glowing. You, me, the chair you're sitting in, we're all emitting radiation right now. We just can't see it because it's in the infrared. But when you crank the heat way up on something, that glow shifts into the colors we can see. And that's the light we're talking about.
And here's where the real challenge came in. The scientists could measure this glow with amazing precision. I mean, their data was perfect. They knew exactly which colors appeared at which temperatures. The problem? Their theories just couldn't explain the pattern at all. In fact, their equations predicted something that was completely bonkers. And we're not talking about a small rounding error here. This was a giant red flag, a sign that the very foundations of physics were cracked. It was a full-blown crisis. This crisis even got a super dramatic name, the ultraviolet catastrophe. And honestly, it wasn't an exaggeration. The problem was that the existing theories predicted that as you looked at higher and higher frequencies of light, past blue and violet into ultraviolet, a glowing object should be releasing more and more and more energy. This graph just shows you what a disaster it was. On the one hand, you have reality, what they actually measured in the lab, a nice, predictable, and most importantly, finite amount of energy. But on the other hand, you have what their equations predicted, an amount of energy that just shoots straight up to infinity. For physics, that's basically a game over screen. Just stop and think about that. If those theories were correct, turning on a light bulb should unleash an infinite blast of energy and, vaporize the entire planet. Since that obviously doesn't happen every morning when you flick a switch, something had to be deeply, fundamentally wrong with the laws of physics. So, physics needed a hero. It needed a whole new way of thinking. And that brings us to the year 1900 and a German physicist named Max Planck, who came up with what he himself called an act of desperation. And this wasn't just another small discovery. It was a huge turning point. For centuries, classical physics was the undisputed champion. It explained planets, pendulums, you name it. But in 1900, Planck's idea drew a line in the sand. This was the moment the quantum revolution officially kicked off. So here's the core of his radical idea. The old way of thinking was that energy was continuous, like a smooth ramp. An object could have any amount of energy it wanted. But Planck came along and said, nope, it's not a ramp, it's a staircase. He said energy can only come in specific, discrete steps, or packets. You can be on step 1, or you can be on step 2, but there is no such thing as step 1.5. Planck gave these little energy packets a name, quanta. A single one is a quantum. And this word, which basically means how much, is where we get the name for the whole field of quantum mechanics. The big takeaway was that the universe at its most basic level isn't smooth, it's chunky. And the really incredible part is that this wasn't just some philosophical concept. He could capture this entire revolutionary idea in a simple, elegant, and unbelievably powerful equation.
This is it, E equals h nu. It looks so simple, right? But this little equation contains one of the fundamental secrets of how the entire universe is built. So let's break down exactly what it means.
All right, first up is E. That's the easy one. It stands for energy. But it's not just any energy. It's the specific, exact amount of energy carried by one single packet, one quantum of light.
Okay, next we have that little V-looking symbol. That's the Greek letter nu, and it stands for frequency. The easiest way to think about frequency is just color. Low-frequency light looks red to our eyes, while really high-frequency light looks blue or violet.
And finally, we have H. This is the secret sauce. It's known as Planck's constant, and it's a fundamental number of the universe, just like the speed of light. This is the crucial number that connects the frequency of light to the energy of its packets. In our staircase analogy, H is what sets the size of each step. And just look at how ridiculously tiny this number is. That's a decimal point followed by 33 zeros. The steps on the universe's staircase are so incredibly small that in our everyday world, everything feels perfectly smooth, just like a ramp. But when you get down to the scale of atoms, those tiny steps are everything.
Okay, so we've got the idea and we've got the equation. Now for the payoff. Let's see how this one simple formula, with its insanely tiny constant, completely solves the ultraviolet catastrophe and puts physics back on the right track.
Here's how it works. The equation says that high-frequency light, like UV light, has a really high energy per packet. Now imagine you're an atom in that hot object. It's way, way cheaper and easier to make a whole bunch of low-energy packets, like red or yellow light, than it is to save up enough energy to make even one single, massive, high-energy UV packet. So it just doesn't make very many of them. The energy output drops way off at high frequencies instead of shooting up to infinity. And just like that, the catastrophe was gone, and the math finally matched reality.
And that is the huge, mind-blowing takeaway from all this. Planck's act of desperation uncovered a fundamental truth about reality. Our universe isn't a smooth, continuous painting. It's more like a super high-resolution digital image made of tiny, indivisible pixels of energy. The universe is quantized.
This one idea just threw the floodgates open for all of quantum mechanics, leading to everything from lasers to computers to how we understand the atom itself. And it leaves us with this one last fascinating question. If energy comes in discrete steps, what else in our universe does? What other things that seem so smooth and continuous to us are actually built from tiny fundamental chunks? The search for that answer is still going on today, all thanks to a simple observation about a glowing piece of metal. Thanks for joining us.